All right, chapter 4, section 6, complex numbers. Complex numbers. So we're taking a little bit of a diversion from what the rest of this chapter has been about solving quadratics. Again, everything up until this section has been simply about, okay, finding solutions, how to solve for x within a quadratic x squared polynomial, right? Whatever that looks like on the graph. And we get those parabolas, those U shapes. But now we're going to talk about a new family of numbers. And this is something I've alluded to in a couple of the other sections, this idea of this will represent that in every section that we covered so far, the no real solution was a possibility. There's a reason why we threw in that word real solution, okay? Real solutions refer to a family of numbers, namely the real numbers. And we never really talk too much about that. You've definitely heard that term before, even if you never really fully understood what it meant. Because for us, the real number family basically represents every single number that we're familiar with, right? However weird a decimal is, however negative or positive whole numbers, weird fractions, though anything that we've dealt with basically up until this point, up until this section, has been in the form of a real number. All right. Now, real numbers are very tangible. They're the numbers that you can do all your operations on the calculator with. And visually, when we're talking about these solutions, relating it back to this chapter, they represent the actual intersections, the real intersections where these parabolas, these U shapes, cross the x-axis. So what are complex numbers? The very fact that there is a family of numbers called the real numbers implies that there's another category of numbers that are not real. And those not real numbers are what we call complex. Now, a complex number, in the most basic sense, is going to have this kind of look to it. A plus bi, where A represents some real number. Okay, so technically all real numbers are also can also be expressed as complex numbers. It's just that this little extra piece right here would be 0. Okay, so like the number 8.7. The number 8.7 is a real number. Okay, it's an actual tangible number. And so in a complex number form, 8.7b, that A would be an 8.7, and then bi would just be 0. 8.7 plus 0 is just 8.7. Okay. So in a complex number form, we have this new term right here, namely this letter I. And I is going to refer to what we call an imaginary number. So if you're like me, the very fact that imaginary numbers exist and the very fact that it's named imaginary it prompts these questions like, why in the world does this stuff exist? Or is this something we're ever going to use? Why would you even create a category of numbers called imaginary numbers? If they're fake numbers, why would you even bother with them? Okay. Now, for the record, I'm not going to get too deep into like the properties and the uses of imaginary numbers. For right now, in this level of math classes, suffice to say that they are useful. All right. And I'll just give you like a little bit of information on it, namely that it is used practically in electric professions and anything basically that has a wave function. Right. And those are terms maybe that you will not be familiar with, and that's okay. And we're not going to get too deep into that for now, but it's particularly useful when you get into trigonometry, calculus, and that sort of thing. When you start dealing with what are called wave functions, we're going to be dealing with only the most basic form of functions in this Math 2 course, and you'll be introduced to 1 or 2 more in Math 3. But once you get into the higher level mathematics, you start to deal with wave functions, and wave functions are everywhere in real life. And those waves can produce what are called imaginary numbers or have imaginary solutions. For our intents and purposes, for chapter 4, they're going to represent those ghost intersections that a parabola doesn't have. Let me explain. So again, what we've come across so far, and let me relate this back to section 2, when we actually visually graphed these parabolas, these quadratics, and we were looking visually for where those U shapes cross the x-axis. Well, if they completely missed the x-axis, then it wouldn't have any intersections, and we would simply put no real solutions, and that's still true. But it does imply that it does have imaginary solutions. All right. And that's where it's a parabola, this U shape, is fundamentally a little bit like a wave function in the type of curve that it has. It's just that a wave function, instead of just going up forever as a U shape, it would go up and then it would cycle back down and then create this wave type of shape. And so because of that, that's where we're going to get these imaginary results, the ghost intersections, all right? And they hinge around this letter I. I for us is going to represent the square root of -1. I equals the square root of -1. Why is this imaginary number the square root of -1? Because if you were to attempt to take the square root of -1 on your calculator, you would get an error message. Because so far in our realm of real numbers, that we can't take the square root of a negative number because there's nothing that multiplies by itself that gives me a negative result. So if I were to take the square root of a negative number, there's no real number. There's no whole number, no negative number, no decimal, no fraction that I can think of that can multiply by itself to make a negative. Even if I had a negative number and I multiply by itself, the negatives cancel and I get right back to positive. So imaginary numbers happen when I do take the root of a negative. So the actual applications of this for our algebraic purposes in this section and in this chapter are actually very, very simple. Anytime I see a negative under a root, I can quickly get rid of that by simply adding in the letter I. And so I give you this little illustration right here. So for instance, if I were to give you the square root of -9, all right, that's the same thing as saying the square root of -1 times 9, right? So -1 times 9, I can get right back to here. And then I can kind of separate these as the square root of -1 and the square root of 9. This came from section 1, our properties of radicals. I can split these guys up. And this square root of -1, again, is this imaginary number, this letter I. And so I is going to be multiplied by the square root of this 9. And this is one that we will be familiar with. This is going to be the plus or minus 3. And so I is going to just be represented here. So really the only thing that got added in here, it's still the square root of 9. It's just that because it's a negative, I'm going to add in this letter I. Pretty much that's the only new thing for us. As soon as we see a radical, a root with a negative number, first off, this will represent no real solutions in our graphing sense, our visual sense of where this parabola crosses the x-axis, but there will be imaginary results that pop out the other side of this. And that just means algebraically, everything is going to be the same. We just add in this letter I. Okay, so let's do a couple of examples. So I'm going to only do a couple from this section's notes, these section notes, mostly because the actual algebra is almost exactly the same as everything we've done so far. It's just that we're going to be dealing with negative roots. And so this letter I is just going to pop up on occasion. So let's see how it gets applied. So first off, part A right here, I'm not going to do, but it's going to be essentially the same exact result that we had for this illustration right here. We know what the square root of 25 is. That's plus or minus 5. The very fact that it's a negative just means I'm going to make it a plus or minus 5i. That's as simple as that one is. I'm going to do part B right here as our illustration, because this will give us a little bit of practice back to what we did in section 1 with simplifying radicals. Your first couple questions will be similar to what we did in section 1, so you can always reference those notes again. But let me go back into this. All right, so we're given this radical. Square root of -72. Now, the fact that I'm dealing with a radical of a negative means I know automatically I'm going to be dealing with this imaginary set of numbers. Namely, I'm going to have I in my result. So here's the simplest way to deal with this right now. And here's what I can do. I can convert this into simply square root of positive 72. But now I would add in this imaginary number I. So as of right now, this is now exactly like something that we did in section 1. and I simplify it the same exact way as before. It's just that this letter I is now attached to it. This I, again, represents the square root of it, that negative result. So I can simply convert it to this, and now it's just like everything we did before. That's essentially going to be the theme throughout this section. As soon as you see this negative in the radical, pull that I out. So now I'm dealing with the imaginary family of numbers, but the algebra after that is exactly the same. So here, relating back to section 1, I would see like, all right, if I try to take the square root of 72, I get a decimal for the record, and that's okay. But if I wanted to simplify this, my job is to then say like, all right, well, if I can't take the square root perfectly of this guy, are there any perfect squares that do go into this? And the answer is yes, there's a couple. I'll go ahead and skip to the punchline, which is what's the biggest square root that goes into this value? All right, many of you would probably see that 9 goes into this, and that's true, but there's a bigger one, 36. 36 times 2 can give me 72. So let me kind of show you what this looked like. Again, this is a relation back into section 1, these examples. All right, but 72 can be rewritten as 36 times 2. So 36 times 2 gets me right back to the 72. And that's important because I wanted to split it up this way, and that letter I is still there because it represents that negative. But I want to split it up this way because this guy I can actually take the square root of. And then again, coming back to that property that we dealt with in section 1, I can split this up into 2 radicals right here, with 2 being under the next one, 36 being under this guy. Okay, that was our property about anything underneath the same radical, and like anything multiplied underneath the same radical, I can split up into each of its pieces. But always remembering that this I is still there, because again, that represents that negative. And at this point, this piece can be simplified. That would be simplified into positive or negative 6, because either positive 6 or negative 6 squared will get me right back to 36. The radical 2, that can't be simplified further. So that stays radical 2, because I can't take, if I were to attempt taking the square root of 2, it would give me a decimal, and there's no other perfect square that can go into 2. And then again, this I hangs out at the back end. That was just the first step to pull that I out. And this would end up being the simplified form of that radical. This plus or minus 6 times radical 2 would be just the same result that we would have gotten in section 1. The fact that it was a negative 72 we were taking the root of is just where this I comes from. So if you want to break this down a little bit further into what like the actual 2 results would be, because again, that's that plus or minus, that would be positive 6 rad 2 I, and your other result here would be that negative 6 rad 2 I. Sorry. So this plus or minus just represents these 2 possibilities. And that I, all that I represents is that we're in the imaginary family of numbers. But everything else within that problem was from section 1, simplifying a radical. All right, let's move on. Let's do another one. So you're going to get another set of questions in your assignment that will look similar to this. Let me pull this up on our notes. All right, so I'm looking at this example right here. All right, so in these sets of problems, you're going to be given this situation. I'll say find the values of x and y, some missing variables. Find the values of x and y that satisfy the given equation. And you're given 2 complex numbers. And again, let me just relate this back to what we had at the top. Both the left side and the right side of this equation take on the form of a complex number, being a, which will represent some real number, and then bi, that I representing the imaginary number. All right, so this is what we would call a complex number. I, again, is the individual I piece. I does equal some value. It does equal the square root of -1, whereas a and b will be any numbers, any other real numbers that we're familiar with. All right, so this one is actually super fast. Let me just kind of illustrate this really, really quickly for you. So we're given this 2x plus 7i equals 10 plus yi. All All right, so this looks pretty scary so far because there's just a lot of letters going on, but the concept's actually very, very simple here. Each of these represents a complex number. Some A, this will be some actual number, and this 10 is an actual number. And then I have some BI, some other real number, but multiplied by an imaginary. So this right here is an imaginary result, each of these right here, attached to that A being and what value this y has to be. Okay, but this ends up being just a very simple concept. Let me actually illustrate this for you. This first term, the piece that does not have an I attached to it, has to match or equal the other corresponding real number piece. So 2x has to equal or match 10. The I pieces, or the imaginary pieces, are the pieces that have I in it, okay, which are the 7i and the yi. Essentially, this is no different than like terms, the things that we've been dealing with for years now. So since both these pieces have an I attached, they have to match on each side of the equation. In other words, 7i has to match yi. All right? So essentially, I end up with these two simplified equations, and yes, it's as simple as you may think. In this case, in order to solve for x, or to isolate it, I would divide both sides by 2, and I'd end up getting x equals 5. Well, that's what x has to equal in this case. On this one, both of them have an I attached to them, so the coefficient multiplied by the I has to also match. And so one way I could think of it is I divide both sides by I so that they go away, and I'm left with 7 equals y. Done. If I were to plug either of these values back in, if x is 5, well, 2 times 5 is 10. If y is 7, right, then that is 7. And I'd end up with 10 plus 7i equals 10 plus 7i. It checks out. Essentially, all you had to do here was combine like terms, right? I's had to match I's, A's had to match A's, or I should say A's had to match A's, and BI had to match BI, whatever B was. All right, well, that was that one. You'll get a couple of questions like that. Again, fairly basic. It's just like terms. All right, let's move on. So now you're going to be asked to do some operations with complex numbers. So I'll do one of these, but again, I just want to show you what you're going to be seeing. So you're going to be asked to either add or subtract complex numbers, right? And again, it will be a little bit scarier because you're going to see some variables, or you're going to see some i's, rather, some imaginary numbers. And you're going to see stuff like this. And it'll be scary because you're going to see these parentheses, and it's going to look like it's pretty complicated. But again, the concept is very simple. Combine like terms. If it helps you, think of I as like the letter X, some variable, in which case you can only combine the I's with other I's, just like you would only be able to combine X's with other X's, and just regular numbers, real numbers, with other real numbers. All right. So in this case, when I add these two together, I have to add that 8 to that 5. I would add that negative I to that positive 4i. Really, the only thing I have to keep track of are the negatives. So let me go ahead and do part B right here, right? Just because a lot of people tend to struggle with the subtraction of two things. So let me do this one, right? So in this problem, we're given the following. We're given 7 minus 6i, and they put it in parentheses, telling us like, all right, well, this group of stuff, right? This 7 minus 6i, I'm going to subtract this other group of stuff, this other binomial, this 3 minus 6i. All right, so my job here is to simply subtract these two items. Well, again, the simple concept here, and if you want to throw this in your margin, essentially all I'm doing is combining like terms. This 7 can only combine with other real numbers, being this 3. This 6i can only combine with other i's, being this other 6i. Right? I just have to be really careful about signs. So what I'm going to do here, anytime I subtract a chunk of stuff, one quick thing I can do is I can distribute this negative in throughout this parentheses. In other words, just flip the sign of everything here. So this first parentheses, nothing's really different with it. Nothing's multiplied by it or anything. So it's still 7 minus 6i. But when I subtract 3, that becomes minus 3. And when I subtract a negative 6i, that becomes subtracting a negative or plus 6i. So really what happened here is this minus just flipped the sign of each of these terms. Just be careful about that. At this point now, it's just combined like terms. 7 and a negative 3. In the solutions, I actually go through the trouble of rearranging this. So I would have, I'll go ahead and write it. 7 minus 3, and then this negative 6i, and then plus 6i. Right? All this is a rearrangement of that same result. Right? You don't have to do that. Many of you would just be like, all right, 7 minus 3, that's 4, negative 6i plus 6i, that cancels. I don't know if it was 0i or 0. But let's wrap this up. 7 minus 3 gives me 4. That's my real number. And then negative 6i plus 6i does give me a result. It just happens to be plus 0i. Technically, this is the complex solution. But it's also worth noting that 0 times I is just 0. In other words, my solution here is also can be just written as 4. All right. Both of these are the same thing. That's an important thing to understand. This is just what we would call the complex number version of that value. We're all familiar with this. This is a real number, something that we're more than familiar with at this point in our math careers. But this is just the complex version of that. 0i just represents that the imaginary piece here, there's just no imaginary piece in this complex number. But that's that result. Just essentially, again, combine like terms. All right. Let's do one more example. This one is going to deal with a different math operation, namely multiplication. But let me show you this. Okay. Again, I'll do the second one here so you can kind of see this. This will be similar to what we did in chapter 2, and I'll go through that process again. But again, we're given some multiplication problems here, and this is no different than what we did in chapter 2. It's still distribution, collection of like terms. The difference here is that now I'm just dealing with these i's. And there's going to be one curveball that I'll point out as I do this example. But this will be our last one for this section. I'll do the second one. All right. So the task is something familiar to us. We're still just multiplying things. The things just will involve imaginaries now. So in this case, we're given 9 minus 2i, which is a complex number. That's a. A is just a positive 9, and bi is a negative 2i. And then we're multiplying now by negative 4 plus 7i, another complex number. If it helps you, you can think of I as like X. And then this is no different than anything that we did in chapter 2, where I'm multiplying two binomials. Well, the process here is going to be the same. Let me just go through this. So this first object, if I multiply it throughout this parentheses, I'm distributing 9 times negative 4 and then 9 times a positive 7i. So in this case, I'm going to end up with, let me write this way, 9 times negative 4, and then plus 9 times 7i. That's the positive 9 multiplied by each of these items. Done with 9. Now I'm going to move on to my next object. This should be familiar from chapter 2. So now I have negative 2i times that first object being negative 4 again. And then I take that same negative 2i and I multiply by the last object. This is the distribution process. All right, getting a little crunched in here, but that's going to be 7i. All right, well, there's the distribution. That's no different than anything we did in chapter 2. It's just multiplying polynomials. So now I just do the actual individual multiplication pieces. 9 times negative 4 gives me negative 36. 9 times 7i, I just combine the numbers here, just like I would if this had been an x. So I'd do 9 times 7, which is plus 36i. That just has an I attached to it. So for the record, these are two different values. This one is imaginary. And then in this case, again, just multiply the numbers. Negative 2 times negative 4 gives me positive 8. The fact that it has a letter attached to it, that just stays a letter, just like if it had been an x. And in this case, negative 2 times positive 7 gives me negative 14. But again, I have I times I. Here's where you need to be very careful. This is the biggest slip up for the students in this section. I times I gives me I squared. We're going to deal with that I squared in just a second because it does not stay I squared. Okay, well, I can combine stuff, but before I do want to deal with this I squared piece because this, again, is the one curveball. This is the one curveball that I want to point out in this section. And here's where I'll direct you again to what we had in our notes. So let me scroll this down a bit, give us a little room. So in our notes, at the top of our notes, we talked about complex numbers and we talked about what I equals. I equals the square root of -1. But if I equals the square root of -1, here's the thing I want to point out. I squared, and I didn't point this out at the beginning, I squared is the square root of -1 squared. But the square root of anything squared gets rid of the square root, and I'm left with that something underneath. In other words, I squared is the only value that if I square it, I get a negative result. So what does that mean in our case? That this -36 stays -36, this plus 36i stays 36i, this plus 8i stays 8i, and then I have -14, but instead of I squared, I'm going to be replacing I squared with -1 because I squared is -1. And at this point, now I can do -14 times -1. That will give me a +14. So everything else stays the same right here. All right, just like as if it was a regular variable. But now -14 times a -1 is going to give me a +14. The negatives cancel there. And that's important because now I can combine these two terms. I have two regular numbers and then I have two numbers that have i's attached. So now I'm just combining like terms. -36 plus 14 gets me to -22. And then 36i plus 8i, I combine that just like any other like terms, and I would get plus 44i. There is my result. Again, the major twist there was that when I came across this I squared, this is where it's different than a regular variable because I does actually equal something. It equals the square root of -1. So that square root of -1 squared gives me that -1 result. And so that's important because this value does change to another regular number that can combine with the other regular number. That's as tricky as it gets for this complex number stuff, is that now I squared is an actual number value. And that's where it is a little bit different than just treating it like a variable because it is an actual number. All right, well, that's the end of section 6. Let me go ahead and stop recording.